Hello. We are looking at topics 3.4 and 3.5, carrying capacity and population growth and resource availability. They're going to be kind of all combined together. So I guess we're going to jump right on in, and I think there's going to be two videos for these two topics all combined together. All right, so let's first say that populations are unable to grow indefinitely, obviously. And that's because of limiting factors. Can you think of any limiting factors right now? Take a second and think. And you're done thinking. Here are some limiting factors. Sunlight, if we're looking at plant growth, water availability, space, competition for food, competition for shelter, competition for other resources, predation, which is obviously what you're seeing here with the great white shark and the some sort of sea lion, can't tell. And disease, just some examples of both biotic and abiotic limiting factors. So again, populations cannot grow indefinitely. There's always going to be some sort of factor that limits their growth. So looking at some different graphs that you're going to be seeing throughout Unit 3 here, we are, in this graph, looking at the intrinsic rate of increase. The x-axis is showing units of time. The y-axis is showing the size of the population. This is a J-shaped curve. And basically, intrinsic growth or intrinsic rate of increase is what could happen if a population has unlimited resources, just like it says there on the screen. But clearly we know in the real world, resources are limited. So this is just kind of like a hypothetical. Here's what could happen based on, the reproductive abilities of whatever organism we're talking about. Clearly, this is not something that happens in the real world because we, again, have limiting resources. So let's talk about rapidly growing populations and some major characteristics that rapidly growing populations have. One, and I want you to think about this before I give you the answer, timing of reproduction. Like, do organisms that exhibit a rapidly growing population, do they start reproducing early in life or later in life? If you said early in life, then you are correct. So organisms that reach sexual maturity early in life, clearly that implies that the population can increase pretty rapidly. Another characteristic of a rapidly increasing population is generation time. So again, think about this before I give you the answer. What is going on with the amount of time between generations? Is it a short amount of time or a long amount of time for a rapidly growing population? If you answered short generation time, then again, you are correct. So, you can have a litter of offspring, and then just a short while later, another litter, and then another litter, or whatever group of offspring you want to call it. So a rapidly growing population is going to have short generation times in addition to reaching sexual maturity early in life. A third characteristic of a rapidly growing population is how long they stay in their reproductive phase for. Are they staying in it for a short amount of time or for a long period of time? If you said for a long period of time, then clearly you were correct. So the longer that whatever organisms we're talking about, the longer they stay in the reproductive phase of their life, obviously, the more the population can increase. And then lastly, my fourth and final characteristic of a rapidly growing population, the number of offspring that are being produced by these organisms. And the number of offspring that's being produced, the general term for that is fecundity. So do organisms have high fecundity or low fecundity if it is a rapidly growing population? If you said high fecundity, you are correct. So lots of babies. And so these are just 4 very broad characteristics that are going to result in a rapidly growing population. All right, moving on. Just kind of bouncing around everywhere here in topics 3.4 and 3.5, looking at carrying capacity, which is designated by the letter K. K comes from a German word referring to carrying something. I don't know what the German word is. It's not important. But carrying capacity is determined by 2 things. One thing, as you can see here, is biotic potential. And so this is just a lot of vocabulary here so far. Biotic potential is, based on whatever organism we're talking about. How quickly, how rapidly can those organisms reproduce in ideal conditions? Ideal conditions would be, like without limiting resources. How quickly can they reproduce? How quickly can that population grow? And the second thing that determines carrying capacity is environmental resistance. Those would be your limiting factors. So those 2 things working together, biotic potential plus what's going on in the environment, that is going to determine the carrying capacity of a habitat or an environment, or even the carrying capacity of the planet. So carrying capacity is going to be different for every different organism in every different environment. As any population gets close to or approaches carrying capacity, the population's rate of growth will go down because the population is using up the resources. As the resources become limited, that's obviously going to have an impact on reproduction rates, and so the population will start to slow down in their reproduction, and then eventually the growth will not only slow down, but begin to decrease. So 2 questions to answer here. As a population is getting close to carrying capacity, what happens to the mortality or death rates in that population? Does mortality go up or down? Give me a second. If you said mortality decreases, you are mortality increases, then you are correct. Obviously, fewer resources is going to lead to more death. What happens to fecundity, or the number of offspring that are being produced? Fecundity will decrease. So mortality goes up and the number of offspring being produced goes down as a population gets close to carrying capacity. Because again, we're just using there's too many organisms using too many resources, and that cannot continue indefinitely. As we look at carrying capacity, perfect spot for my picture. We often, again, looking at graphs, we sometimes see exponential growth. Again, just look at the graph. X-axis is time, Y-axis is the size of the population. Exponential growth is a J-shaped curve, just like the intrinsic rate of growth. It's not really realistic because obviously every population is going to have a limit where that exponential growth can no longer continue. And speaking of exponential growth, you should know this equation for calculating the size of a population that is growing exponentially. You may have seen this in like a finance class, because this is the same equation that you'd use to calculate interest. So what do all these letters mean? Let's look at it in the next slide. Moving myself over. So n sub 0 is the time of 0, the beginning population size. R is the growth rate. E is a constant. Technically it's 2.7. Time is t, and n sub t is your final population size. Again, like I said, this is how you can calculate interest as well. So let's do some practice calculations here. So take out your calculators, because you are going to need to know how to do this. So let's say that we have a population of mice, begins with 20 individual mice. The growth rate is 20%, or if you convert 20%, it's 0.2. Calculate the size of the mouse population in 5 years. So get a piece of paper or something out so you can do your math. Again, we're using this formula. N sub t, that's what we're calculating, is the final size of the population. So we're starting with 20 individuals. That's what you see here. And then the growth rate is E. You can also, on your calculator, E is going to be, what is it on your calculator? E superscript X. You can use that function on your calculator. 0.2 is your growth rate, and 5, we're talking about what's the population is going to be in 5 years. So 0.2 times 5, if you multiply those two exponents first, is 1. This is a 1, not a letter L. Again, 2.7 is that constant, so 2.7 times 20. The final population after 5 years is going to be 54.4 mice. I know you can't have 4/10 of a mouse, but we're just going to leave it as a decimal here. So let's say we're continuing with this exponential growth, and we want to know what the population is going to be not in 5 years, but in 10 years. Again, use the same formula. 20 is my original population size, 2.7 is my constant, 0.2 is my growth rate, or R, and we're looking at what's going to happen to the population here in 10 years now. So 10 times 0.2 is 2, and then 2.7 squared times 20 is going to give you a total of 147.8 mice. And you do need to know how to do this for the AP exam. They will not give you a formula sheet, so this might be a formula that you either need to memorize, or if you have a graphing calculator, plug it in to your graphing calculator. And so my final example here, again, still using this population of mice. Now let's see what would happen to the population in 20 years. So we went from 5 to 10 to 20. That is exponential growth. 5 years, double it to 10 years, double 10 to 20 years. And that's what exponential growth is all about. So 20 times 0.2 is 4. Do your final calculation, and you'll have a total of a little over 1,000 mice. So again, this is one formula that you will definitely want to know, not only for exams in class with me, but also for your AP exam when you take it in May. So if you have any questions about this math, obviously let me know. There is going to be some more coming in the next video. I'm just going to finish this up. I don't have much time. So we've got exponential growth, and then the other side of the equation, we've got logistic growth. This is more realistic, where we begin with exponential growth in the early times. Eventually that exponential growth flattens out and becomes what we call an S-shaped curve, where the population kind of plateaus somewhere around carrying capacity. And this is much more realistic than exponential J-shaped curve. I think I'm gonna leave it at that, and we'll come back in the next video because my videos are limited to 15 minutes. We'll come back in the next video and take it from here. So, as always, if you have questions, ask me. Ta-ta for now.